welcome to the Rockwell lecture, which the distinguished lecture was sponsored by the College of Engineering. Today it coincides with our Friday Buyer lecture. I want to introduce Dr. Pedro, Professor Pedro J. Alvarez. He's the George R. Brown Professor of Civil and Environmental Engineering at Rice University. He also serves as founding director of the NSF Engineering Research Center on Nanotechnology Treatment, and as director of the Rice Water Institute. For the students out there, the National Science Foundation awards extremely competitive large centers called the ERCs, and Professor Alvarez is the leader of one of these. He won it a few years ago, if I remember correctly. Professor Alvarez's research interests include environmental implications and applications of nanotechnology, bioremediation, fate and transport of toxic chemicals, water footprint of biofuels, water treatment and reuse, and antibiotic resistance control. Professor Alvarez is an executive editor of the top journal in environmental engineering, which is called Environmental Science and Technology. I'm proud to say that many of our faculty in our department publish in the journal. And he previously served on the scientific advisory board of the EPA and of the advisory committee of the National Science Foundation Engineering Directorate. In addition to conducting pioneering research, Professor Alvarez has made significant contributions to both his communities and education. This includes service on the board of directors of the Houston Endowment Corporation, which is a private foundation to improve the quality of life for the residents of Greater Houston. And he also served as a transformative educator at Rice University, as evidenced by being selected for the Rice University Collegiate Excellence in Teaching Award, the Perry McCarthy Association of Environmental Engineering and Science Professors Founders Award for outstanding contributions to environmental engineering education and practice, and also serving as president of the Association for Environmental Engineering and Science Professors. Professor Alvarez has a very long list of awards. I'm not going to list them all, or I'll take an hour of this time, but I'll just limit to myself to the fact that he's an elected member of the National Academy of Engineering for outstanding contributions to the practice and pedagogy of bioremediation and environmental nanotechnology, to election to the American Academy of Arts and Science, and also election to the Chinese Academy of Engineering. So with that, Pedro, thanks for coming.
Thank you. Well, thank you for that very kind introduction. I am very honored to be here and also very happy to see so many friends, Pradeep, Roberto, Halea, and I saw a little while ago my long-term collaborator, Bill Rixey. Congratulations on an excellent career. I am sad to see you retire, but happy for you at the same time. Today, I would like to share a vision of how nanotechnology can help us achieve water security. And these are going to be examples from our Newt Center, and I have to acknowledge that actually I'm going to be presenting mainly research that my lab was associated with, because that's what I'm most familiar with. But there is a lot of stuff that I'm not going to talk about that was conducted by excellent researchers from our partners from Yale, ASU, and UTEP. So let me see. Yeah, this works. Let me begin by pointing out that although we live in a water-abundant planet, with 71% of the surface covered by water, the fraction, very small fraction, is available for human consumption or to grow food. I'm talking about 0.014%. And that small fraction faces significant competition by different users for different uses, which reminds me of what Mark Twain used to say, that whiskey is for drinking and water is for fighting over. And unfortunately, ensuring affordable and reliable access to clean water is getting harder because the demand for it is growing with an increasing population and changes in lifestyle. Because water pollution by a wide variety of emerging pollutants, both chemical and biological, are becoming more difficult to treat. And on top of that, we have climate change with more frequent droughts and extreme events, and even sailing intrusion in coastal areas that are exacerbating freshwater scarcity. I always like to emphasize that clean water can save more lives than doctors, and this is an example of it. Life expectancy of Americans at birth was 47 in the year 1900, and thanks to disinfection and enhanced sanitation is now at 78 years old. That's what I call working on the correct side of the decimal point, right? But we have not won this war yet. We still have half of all hospital beds in the world occupied by someone who got sick by a waterborne infectious disease. In the US, we have 43 million Americans not connected to municipal water systems, mainly in rural areas. And the bottom billion still in the world still lacks access to clean and safe water. Furthermore, our urban water infrastructure is failing to reliably protect public health and support economic development, which underscores the need for technological innovation. And among the challenges that we face, well, first, we use way too many chemicals that generate waste streams. And some of those chemicals, for example, used in disinfection, generate carcinogenic byproducts. Also, we have very old and deteriorating water distribution system, especially in Houston, where we lose about 16% of the water, to leaks. Also, we have the problem that they serve as breeding grounds for opportunistic biofouling pathogens. And we also have to deal with a lot of contaminants of emerging concern. I'm talking about endocrine disruptors that bypass the treatment process and affect our hormones and our fertility. And I'm talking about forever chemicals like PFAS that are showing up in the blood of newborn babies. Another challenge is insufficient resilience of water supply. That's a major issue. In the United States, roughly one water main breaks out every 2 minutes, and we lose 7 billion gallons every day. That's roughly 16% of the total water supply. Houston, again, is particularly troubled by that. But in Texas, you may remember, the power outage in 2021 that resulted in 15 million people affected by this, and they had to issue a water boiling warning to basically protect us from infectious diseases. On that note, energy for water treatment and distribution is a major sustainability challenge. About 20% of the electricity that we consume in most cities in the US is used to deliver treated water. And what this to me tells me is that decentralized or distributed treatment offers an opportunity to match the consumer location to alternative water sources. And this is a way to minimize energy and water losses through these old and leaky systems. But also, sorry about that, I didn't pass this. But also desalination, which is a growing necessity, is also a big energy concern in that, for example, over 1/2 of the cost of seawater desalination by reverse osmosis is associated with electricity consumption, underscoring the need for alternative desalination approaches that use less energy, right? Anyways, our center vision is to enable access to adequately treated water by developing this next generation of modular treatment processes that would be empowered by nanotechnology so that they are smaller and easier to deploy, and so that they have superior treatment capacity to essentially treat challenging and industrial wastewater and reuse them. And our aspiration is to create clean water on demand, again, which may require tapping or reusing unconventional sources. And we want to do that using less energy and less chemicals, right? So what we are advocating is for something that we call distributed fit-for-purpose treatment. And I will explain what that means, but first let me give you our motivations. First is that we have no choice. We just don't have enough infrastructure in expanding megacities or in rural areas, and have to rely on distributed treatment, not just for municipal, but also for industrial, like in the Permian Basin, for example. But also, distributed treatment gives you the flexibility to match the treated water, to match the location of the consumer, and basically avoid long-distance transport will save energy. But most important, I think, is that flexibility to match the treated water quality to the intended use. That's what I mean by fit-for-purpose treatment. If you're going to use the water for irrigation, there's no need to remove nitrogen and phosphorus, for example, right? And this is a great opportunity for nanomaterials and other advanced materials to enhance the selectivity of the process so that you can remove with higher precision those pollutants of greatest concern, and also to introduce multifunctionality so that you can simultaneously remove different classes of pollutants, which facilitates the development of smaller and more robust treatment systems that minimize also energy requirements and chemical usage. And to reinforce this choice for modular and distributed treatment, let me make a very simple economic argument, right? The general belief is that the cost of water treatment will decrease on a per volume basis as you increase the size of your treatment plant due to the economies of scale, even though the cost of delivering it, the conveyance cost, increases with the size of the system. And we end up trying to minimize the total cost, which is system specific. I call it the levelized cost of water. By that I mean the life cycle cost that considers capex and operation expenses normalized to a unit. For example, dollars per liter that you deliver to your tap, and it's very system specific minimum. My argument is that if we were able to decrease the cost of treatment at the small scale, at the point of entry, at the point of use in a building or in a maybe hotel or even neighborhood, we might be able to decrease the levelized cost of water. And we can do this by taking advantage of the higher selectivity and multifunctionality that nanotechnology allow us to implement so that we don't treat waste treatment capacity on things that don't matter. And that is what we call our technology opportunity zone. Small, distributed, fit-for-purpose treatment and reuse. Many people ask me at the beginning, mainly, well, why are you using nanotechnology? I mean, that sounds a little exotic. And the reason is that many nanomaterials exhibit very unique, I would say even extraordinary size-dependent properties that are only found at this scale. For example, on a per atom basis, many of these materials exhibit much higher reactivity on a per atom basis, again, than their bulk counterparts. Take gold, for example. We use it in jewelry because it's inert and doesn't corrode. It's passive. But at the nanoscale, it becomes a hypercatalyst. And carbon is a good insulator, but at the nanoscale, it can become a superconductor. So that means you can use these materials for highly reactive advanced oxidation or high advanced reduction processes. An obvious thing is their high surface area. This allows you to develop very high capacity adsorbents, and you can manipulate their surface chemistry to enhance their selectivity towards what you want to remove with most urgency. And maybe perhaps engineer the surface so that the adsorption site is right next to a reactive or catalytic site. I call that trap and sap for more efficient utilization and degradation. This is the kind of multifunctionality that we're after that is enabled by nanocomposites. But perhaps most importantly is the quantum effects, this idea that these materials behave both as a particle and as a wave, and that allows you to exploit the full electromagnetic spectrum for water treatment. For example, we can use sunlight to generate heat using nanophotonics and use that heat to distill water and desalinate much cheaper. And we have a startup on that Chillingly developed. But I'm going to give you 3 examples in general to demonstrate these properties. I'm going to begin with photocatalysis. Photocatalysis receives a lot of interest in the academic world. There's been decades of promising papers showing that this is great. But guess what? Nobody uses it at the municipal scale. Very, very few people. And the reason is cost. I mean, it is highly inefficient. And to give you an example of the light energy that you require to power those lamps, only about 1% of that energy ends up generating reactive oxygen species like hydroxyl radicals that do the job. And of the hydroxyl radicals that you generate, less than 5% of them find their target. Most of them are scavenged by carbonates, natural organic matter, and other things that don't matter. So you're wasting a lot of treatment capacity. These numbers, by the way, are summarized in this article where a friend of mine, Jae-Hong Kim from Yale, played a joke on me, drawing me as a mean boss here in the red shirt. But the point I'm trying to make is that we decided to address this inefficiency by enhancing the selectivity of the photocatalytic process. And I'm just going to show you what we did with titanium dioxide, because titanium dioxide is cheap, it's $1 a pound, is earth abundant, and is generally regarded as safe. In fact, many people use it as a food colorant. In powdered milk or in those white donuts, it's not all sugar. Sometimes it has some titanium dioxide. So anyways, let me remind you of how this semiconductor photocatalysts work. When irradiated by UV light or light of the right wavelength, that excites an electron to the conduction band, which generates a electron hole that oxidizes water and generates hydroxyl radicals that tend to accumulate on the hydrophilic surface of titanium dioxide. Many of the target pollutants that we go after are at least moderately hydrophobic. I'm going to use this endocrine disruptor as an example, bisphenol A, very ubiquitous plasticizer. Has very little affinity for the surface. So for this to work, the hydroxyl radicals need to get away where they get diluted and scavenged. And of course, the effective concentration of ROS, reactive oxygen species, decreases, and so does the rate. So we were thinking, how do we bring the bisphenol A closer to the war zone where you have higher concentrations of hydroxyl radicals, so that you are effectively increasing both the concentration of the pollutant and ROS, and the law of mass action would tell us, well, the rate will increase. We try to do that. It's not easy because, of course, the surface is hydrophilic. And our approach was to partially coat the surface of TiO2 with this common natural polymer, cyclodextrin. It looks like a bucket. It has a hydrophilic outer surface, but the hole, the bucket inside, is hydrophobic, and bisphenol A could fit inside, close to the photocatalytic site. And we partially coated titanium dioxide, again, using a simple refluxing method. What we ended up making are nanosheets, hierarchical spheric particles that are sufficiently large. They're made of nanosheet to preserve high surface per volume ratio. And they're micron size so that you can very easily separate them with low pressure filtration and reuse them. One of the tricks of nanotechnology is to enable reuse to amortize the cost of the materials, right? And in here, we're looking at something that to me looks like a flower, right? Except that this is more like a Venus flytrap flower. The fly is the green bisphenol A that gets absorbed in close proximity to the photocatalytic site where the hydroxyl radical attacks it and doesn't get diluted or wasted on something else. And the benefits of that coating are obviously here, where you can see that when coated, the rate of degradation, the K value, increases by 5-fold. What that means is that you need shorter contact time to get the job done, meaning you use less energy to get the job done. In fact, the electrical energy per order of reaction, which is an important parameter to assess energy efficiency, decreased by 5-fold. Now, the bad news is that this coating, being organic, also gets degraded by the hydroxyl radicals. In fact, after 500 hours of continuous UVC high-intensity radiation, it begins to deteriorate. So what we did is we cross-linked this with a fluorinated polymer. We made sure that the polymer was not releasing fluoride or, basically was robust and, this is not PFAS. And serendipitously, that new polymer coating not only increased the absorption capacity, but also the absorption rate. And of course, it also increased the durability by several multiple cycles by which this was degrading bisphenol A. And we call this strategy trap and zap, by the way. I'm talking about proximal absorption to reactive sites. And we also implemented it to combat the spread of antibiotic resistance from wastewater treatment plants. You see, I learned in doing some research, field research in China, that many wastewater treatment plants serve as breeding grounds for superbugs. I'm talking about multi-drug resistant bacteria, that even though you kill some of them in the last disinfection step, they release antibiotic resistance genes outside of the cell that get stabilized by clay in the receiving waters and in the sediments. And there, they transform those genes into indigenous bacteria, which ends up increasing the environmental resistome. So it's very important to prevent the discharge not only of the bacteria, but also destroy the genes. So using a similar approach here, we use a different catalyst. In this case, it was a bismuth oxide photocatalyst. And we coated it with reduced graphene oxide, which had high affinity not only for the bacteria, but also for the genes that the bacteria would release upon lysis to, again, mitigate their dissemination in the environment. I'm going to move on to the second example, which is PFAS. As you know, these are ubiquitous emerging pollutants that are showing up even in the blood of newborn babies. And they're so resistant that we call them forever chemicals. And incidentally, they were developed in the 1940s by the Manhattan Project to enhance the enrichment of uranium. And their use diversified, and so did their incidental and accidental releases. So now we have a big concern about their environmental pollution because they can cause various chronic health effects and cancer. In fact, I don't know, what time am I supposed to finish? I'll tell you something that will be published this week in ESNT. I found that PFAS residuals at parts per billion in water distribution systems promote biofilm formation and virulence. And these are denser biofilm because of the oxidative stress that they cause, that they are more difficult to disinfect and eradicate. That's one of those overlooked, unintended impacts of emerging pollutants. It's not just the effect that they cause directly to your body, it's the indirect effects, such as augmenting the pathogenicity and microbial security of your waters in this case. But anyways, in the US, we promulgated by the EPA the most stringent water quality standards for any pollutants ever for a couple of these PFAS. Talking about 4 parts per trillion for PFOA and PFOS. This MCL is like having 4 drops of water in 1,000 Olympic pools. It's like trying to find somebody that you don't know on 30 planets Earth. Good luck with that, right? So they're very difficult to detect, let alone remove. And there was a recent analysis by Global Water Intelligence that showed that the most commonly used and technology-ready approaches are based on separation. I'm talking about activated carbon, filtration by reverse osmosis, or sometimes even ion exchange. And the problem is that these are techniques that just separate and transfer the problem from one phase to another. They do not eliminate your toxicity and your future liability. So we favor degradation approaches, and many of them at a very relatively early stages in development and could greatly benefit from basically to face their scalability challenges from basic understanding of their mechanisms and their merits and limitations. So that was the motivation for what we were doing. Many of these emerging technologies, by the way, are advanced oxidation processes. And they rely on reactive oxygen species such as hydroxyl radicals or superoxide to degrade the PFAS. And there was a lot of debate in the literature of whether they work and how well they work and what their relative importance was. So we decided to study this and found that even under highly favorable, highly exaggerated conditions, like unrealistically high concentrations of hydroxyl radicals or superoxide, nothing happened. They could not initiate degradation. Of course, I'm not saying that they're not helpful, these hydroxyl radicals and superoxide. If you degrade it with the first step with something else, they can attack byproducts and help with the fluorination, but they do not work by themselves. And it's a negative result, obviously, but we publish it. Not because I am an editor of ESMT, but because this is actually resolving a controversy in the literature. And it's also, to a certain extent, informing practitioners not to waste their time on advanced oxidation processes that rely on this radical like Fenton's treatment, and to look for other reactive species to get it done. So along those lines, we serendipitously discovered that chlorine radicals that are easily generated by things that you have in every water treatment plant, that is UV and chlorine. You irradiate chlorine with UV, you generate chlorine radicals, and the chlorine radicals can promote some defluorination. We now know that the mechanism involves, and this is very common to many advanced oxidation processes. You remove one electron from the carboxylic end of the molecule of PFOA, and that completely destabilizes it and it falls apart after that. And that's what chlorine is doing, and it's initiating the well-known DHEH pathway. That stands for decarboxylation, hydroxylation, elimination, and hydrolysis mechanism. So this is one alternative, but we're more interested in advanced materials, to be honest with you. We think that would be a more robust approach, because I worry about chlorine radicals reacting with something else and chlorinating who knows what, and having some collateral damage of creating something carcinogenic. So Mike Wong, talking about advanced materials, discovered serendipitously also that hexagonal boron nitride, which is widely used in industry for its lubricating and thermal properties, is actually known as the white graphite, is abundant and is cheap. He discovered that this has photocatalytic semiconductor properties, and that he discovered a new use for them, which is oxidative defluorination of PFOA. And Tom Senfeld, another member of our faculty that specializes in molecular modeling and density function theory, discovered that the action happens at the electron hole that you generate when you excite this hexagonal boron nitride. You see, the hole is hydrophobic. And that's very important, because that means water doesn't get in and compete for that oxidation capacity. Water, a lot of times, competes with reactions. Stacy knows very well, coming from Greg Lowry's, that when you're using zero violent iron to reductively dechlorinate TCE, water is competing for those electrons, and in a similar manner, water can compete with these reactions. So having a hydrophobic hull is very important, and we demonstrated that by scavenging the hull with EDA and stopping the reaction. And one of our partners is Purifics. They're a Canadian company that makes photoreactors, and we tried it with that photoreactor to go to sort of a semi-pilot scale, and found that if you provide sufficient time, you can get complete defluorination. The removal is much faster. You get removal in 1 hour, but you gotta wait about maybe 7 hours or so to get full defluorination, which is possible. But what is important here with HBN is that most catalysts are significantly inhibited by salt. This one is not, which means that if you have PFAS in reverse osmosis brines, which you're not going to be allowed to discharge into the ocean anymore if they have PFAS, you could treat the brines from IX or RO, from ion exchange. And I'm just going to also show you one final example of what we do with PFAS. This one is in my lab with Dino Villagran, and it's electrocatalytic treatment. Also using the trap and sap approach. In this, I like electrochemical systems because they're tunable. You can just turn on the current up and down and get what you want to a certain extent. Here we use hexagonal boron nitride again, but not as a catalyst. We use it as a hydrophobic coating on the electrode, on the anode, to essentially promote absorption of the hydrophobic tail for proximity. And we use a very well-known metal organic framework called UIO 66. It's called that because it was invented at the University of Oslo in Norway, to enhance with the trapping function. We found that a molar ratio of 1:1 MOF to HPN worked best. And decorating HPN with the MOF resulted in the best performance in terms of removal and extent of defluorination. The MOF alone is not very conductive, so it really didn't help at all. But you can see the point I want to make is that we were able to defluorinate with a voltage of only 1.8 and 1.9, which is very low. There was zero removal and zero defluorination without this coating. Again, exemplifying the benefits of the trap and sap strategy. And the EEO, in this case, by the way, was 6 kilowatts per cubic meter, which is excellent, very competitive with other technologies in terms of energy efficiency. You always got to keep that in mind, to be scalable. You got to know what the performance metrics should be. And in our case, I think we met it. But I want to summarize that this, what I call trap and sap strategy, relies on separating your target pollutants from interfering compounds that will scavenge your treatment capacity and concentrating them near reactive sites for more energy efficient degradation. And there are many strategies that you can do that. You can create physical barriers for size exclusion, keep away large things like natural organic matter from the surface so that it doesn't occlude the reactive side. You can engineer and manipulate the surface chemistry of the catalyst. You can make it hydrophobic to attract the tails, or rely on electrostatic attraction of the anionic sulfonate or carboxylic heads. You could even try molecular imprinting. We did that for developing COVID sensors, right, to rely on shape complementarity to enhance with the trapping function. I'm going to move on to the last example, which is biofilm and biofouling control. Biofilms are a big concern in water treatment and storage system because they may harbor pathogens. And they also may accelerate, corrosion, both of which are multi-billion-dollar problems. And biofilms are a big problem if they form, because getting rid of them is so hard. You add a chlorine or a disinfectant, and you only kill the outer layer. The inner layer is protected by diffusion limitations. So we want to try to prevent them or eradicate them after they have been formed. So much of what I'm going to show you today involves bacteriophages, which are basically viruses that exclusively infect bacteria. They cannot infect humans or insects or protozoa or plants, only bacteria. So from that point of view, they're safe. We are pioneering many applications of phages in environmental engineering, including what I'm going to talk about today, which is biofouling control. And I will tell you that even though they are the most abundant biological resource on Earth, about 10 to the 31 on this planet, I think that they are by far the most underutilized biological resource. I view them as green disinfectants in the sense that they're self-replicating green biocides that are highly precise. And this idea of phage therapy was actually pioneered by this guy, Félix Derel. He was sort of French and Quebecois at the same time, and got kicked out of Yale, ended up in Georgia, Tbilisi, Georgia, and in the Liava Institute. And he used phages to fight disease, to fight human pathogens. To be honest with you, Western medicine sort of ignored it for many years. But now this forgotten cure has come to the surface because of so many antibiotic resistance infections where antibiotics just cannot help. And there are now already many commercial products that have been developed to fight human pathogens or even plant pathogens for agricultural applications. We discover a way. The problem with phages is that they're very selective and only one phage will kill one bacteria. And maybe the function that you want to disrupt is caused by thousands of different species, right? But we figure out a way of isolating polyvalent phages that can actually infect multiple classes of bacteria. And even such polyvalent phages have a hard time penetrating biofilms, even though they do better than normal phages. They need help, but we want them to reach the bottom of the biofilm, the root, to attack it from the root and de-anchor it quickly. That's our goal. So to get them a little help, we conjugated them with super paramagnetic nanoparticles. Directional immobilization was important to make sure that the tails that recognize the bacteria are pointing outside. And these are particles that can be pushed very easily with a weak magnetic field. And then you can exert directional control, make them go right or left. And when you're done, you can reverse the magnetic field and pull them back out for reuse. We're using, this is food-grade magnetite that is used to make chocolate darker, so there's no concern about adding something toxic. This is a food colorant. And you can see them here. They're targeting this bacillus. These nanoconjugate nanoparticles with phages are these tiny little spheres that are attacking and destroying this bacteria. And it worked pretty well. You can see here an epifluorescent image of a biofilm. This is the biofilm that has been treated with the particles alone, no phages. And nothing really happens other than some physical disruption as you push the particles in and you pull them back out for reuse, but there's no really effect because this is essentially rust. It's not toxic to the bacteria. Our phages did amazingly well because they're polyvalent and they happen to pack their own depolymerase enzymes, which is very rare for phages. But they didn't do as well as when they were conjugated with nanoparticles and were what I call magnetic Trojan horses. You know, the nanoparticle is like a Trojan horse that is delivering them home to de-anchor this more efficiently. Now, I'm also very interested in solving problems of the developing world. Some people call it the global south. And in this case, the problem I was addressing is biofouling of water storage units. You probably have seen that in many places you have a water tank made of plexiglass on top of the roof. And if you don't take care of it, biofouling develops and then you can get gastrointestinal disease and so on. So in this example, what we did is we use a smart, if you wish, responsive polymer that swells when a biofilm-induced decrease in pH happens. See, biofilms produce fatty acids that decrease the pH locally, and that's enough to swell the biofilm. And when the biofilm opens, it releases the phages that were nano-encapsulated inside. The polymer has a very difficult name to pronounce, but I'm going to give it a shot, okay? It's called tripolyphosphate and glycidoxypropyl trimethylthoxysilane. There you go. And what I want to point out is these are the nano-encapsulated phages. When you artificially, in tap water, you put it for a month, right? And you artificially decrease the pH of the tap water, phages are released, and they're viable. So I know from here that at least they stay 1 month alive and active. On a separate project that I'm not showing you here, I was interested in encapsulating phages on the spores of Bacillus subtilis because I wanted them to last without refrigeration for a long time. And they actually stay viable for over a year. So I think that they can last a lot longer there. But the point is this: if I use confocal microscopy with the SNAR4 dye that essentially produces red dots when the pH decreases to 5 or lower. I can see several areas where the local pH is sufficiently low to cause that swelling and automated, autonomous release of the phages, right? And these encapsulated phages can be easily coated onto susceptible surfaces, such as the bottom of these water storage tanks, just using a simple plasma treatment. And the important thing is that when they're released, they're attacking the biofilm from the bottom up. They don't have to deal with diffusion limitations from a top-down attack. It's the nascent biofilm, as soon as it begins to form, it gets eradicated. And that's a big advantage. And you can see here the benefits of that coating. I mean, this is uncoated against biofoul. If I coat it just with the polymer, with empty shells, if you wish, with no phages, nothing happens. But with phages, you have a significant decrease in biofouling. Before I end, I want to make a comment. One lesson I learned about ERCs are tasked. They have a hidden agenda, right? They are supposed to be economic engines and enhance our global competitiveness. And they expect you to get ideas to market. And then I realized that that's like climbing a mountain with 3 valleys of death. The first valley of death, which is the valley of the idea, is usually where we live, where we come up with ideas and we de-risk them in our labs. But then you gotta take them to the second valley of death, which is the valley of the prototype. This is where you have incubators and accelerators where you work with angel investors and venture capitalists, but also with industry. And it is so important to begin to talk to them even before you begin the ideation process, so that you understand what the real needs are, and so that you have people that pull what you push. Nobody should be pushing anything where you don't feel a pull. And of course, the third valley is the deployment of those big ticket items that here got demonstrated to be techno-economically feasible. This is where you kick the tires and got data to do the techno-economic analysis, and usually this involves either large corporation or big state funding. But my point is that we mainly build this bridge. And as educators, we also are supposed to try to get more people to the top. And the only way to do that is to encourage more people to attempt that climb. You were asking me, do we recognize entrepreneurship in the P&T? And I think we should, for professors, count their patents as if they were paper sciences, right? And also, we sometimes in our center provided some entrepreneurship training, like teaching them how to write a business plan and do customer discovery and so on. And using these principles, I think Newt became a very effective innovation ecosystem. I like to think about it as a one-stop to find solutions to complex water quality problems. We counted with up to 30 faculty labs across the 4 universities. In the 10 years that we operated, we published over 900 papers, many in high-impact journals. We had a lot of spin-off companies. Our economic multiplier was 7-fold. Typical federal investment in research is 1.5 to 2-fold. Ours was 7-fold. And we're very proud of our workforce development efforts, including the placement of 42 new faculty members. So anyways, with that, I want to conclude with my take-home message is that nanotechnology offers the potential for disruptive beneficial innovation, not only for drinking water treatment, but also for wastewater treatment and reuse. And we can develop advanced materials and enabling technologies, such as this listed here, that can be integrated into compact high-performance modular systems. Now, Steve Jobs used to say that people don't know what they want until you showed it to them. And about 15 years ago or so, he showed us smartphones. When I came to Houston, I didn't have one. I didn't know I needed one. And now it's difficult to function without one. And in a similar manner, these smart systems that we're trying to develop we hope will be like the smartphones of the water industry in the sense that they will be able to give you superior multifunctional service even without limited infrastructure. Now, before I end, I would like to announce and invite you to the Leading Edge Technologies for Water and Wastewater Treatment Conference. This is the flagship conference of IWA, of the International Water Association. It's going to come here to RISE on the first week of June of 2026, just a week before the World Cup. So hopefully there will be a lot of people in Houston. And what is unique about this conference is that it brings together leaders from academia, industry, utilities, and consultant, the whole value chain, which is very rare to find in the same place. So the deadline for abstract submission is, November 1st, but of course, I know you guys do great work, so if you ask me for an extension, we'll be happy to do that. But I really want to invite you to submit and attend, especially students. It will be a great opportunity to meet a lot of international leaders. With that, I want to conclude by first thanking the National Science Foundation for funding NEWT. I want to thank the students in yellow that generated most of the data that I presented today. And of course, I want to thank you for your kind attention. Thank you.